Good afternoon. As every Wednesday, it is a pleasure to have you with us. And let me introduce you, Mr. Farhan. To do so, let me read a excerpt from our speaker resume. It said something like that. Farhan Yousaf is a PhD candidate in energy at Escuela Superior de Física y Matemáticas del Instituto Politécnico Nacional en México. He holds a master's degree in chemistry from Lahore University on management science in Pakistan. His research focuses on thin films, solar cells, particularly the processing and characterization of materials for photovoltaic applications through experimental and theoretical. He has experience in catalysis synthesis for water splitting and has contributed to various academic and outreach initiatives in the education and renewable energy sector. Thank you very much, Mr. Farhan, for staying here and dictate the conference today.
Thank you.
Well, we are all ears to
Okay.
you about the topic photovoltaic devices, evolution, challenges, and future prospects.
Okay.
Thank you for staying here. Thank you so much.
Okay. Hello, everyone. Good afternoon. I hope you can listen my voice clearly. I hope I will talk in a loud enough to basically communicate with all of you. Okay. So thank you so much for inviting me this seminar, and thank you so much for attending this seminar. Basically, this seminar is related with the photovoltaic devices. We will see the evolution, the historical background, and also we will see the challenges that we have with this kind of technology. And also we will discuss the future prospects, the research the research lines that now basically the researchers are now focusing on. And let me introduce my name again. My name is Farhan Yousaf, and I'm from Pakistan. Basically, I'm working under the supervision of Dr. Lourdes and Dr. Michael Curl. Okay, let's start. So first, we will go through this energy, spectra. Okay, so we can see that in the early histories, we were depending basically upon mainly on fossil fuels. This one, natural gas and coal, to basically generate electricity. The main source of electricity is basically through these things. The main problem with this conventional energy source or the fossil fuel is when we consume fossil fuel, it produces different kind of gases like nitrogen-based oxides, sulfur oxides, or carbon-based oxide, and that impact our environment. You basically know the term global warming, and the main reason for this is basically carbon dioxide, and that is basically produced by consumption of fossil fuel. So this is a challenge for the scientists. So we need to basically figure out the other ways, the other possibilities to create electricity and to fulfill the demand of a global demand. Okay, so scientists gradually shifted their focus from coal and natural gas to hydropower, solar, and wind. And you can see over the years the gradual decrease of usage of coal and natural gas to produce electricity, and gradual increase of basically production of energy from these two techniques, the solar and wind. And if you can see in 2022, we have seen a rapid growth for this kind of technology, the solar cell technology. And in 2022, we can see that it surpasses the solar energy, the wind energy. And according to basically this report, we can see that for the 2027 projection, the two renewable energy sources like solar and wind will produce almost 20% of the total global demand. and that will basically reduce the usage of coal and natural gas, and that will basically help us to reduce the basically concentration of carbon dioxide and the other gases that are basically impacting our environment. Okay, so with this we can see that solar energy is one of the most important part for the global energy system. Okay, so before going further, we will basically have a look on solar device. I will explain in a very simple words how solar cell basically work. So when we talk about the solar energy, we basically know that solar cell basically convert solar radiations into electricity. And when we talk about the solar radiations, we know that solar radiations, the rays basically consist of photons, and photons basically have energy. So when these photons impact the surface of the solar cell, it get absorbed by the material we call absorbing material. We have different kind of absorbing material. We will basically go through different kind of materials later on in my presentation as well. So when these photons absorbed by the absorbing material, it basically help to excite electron. And when we have excitation of electron, we have electrons and holes. We have electron and holes. Okay. And in our device, we have N-type material and P-type material. N-type material we know basically rich of electron, and P-type is basically rich of holes. So with this, these basically materials help to basically transfer these charged particles towards the electrode. And once they basically move towards the electrode, we have flow of charged particles through outer circuit, that is called the current. So that is how we basically produce electricity through solar radiations. Okay, this is a very simple way to basically explain. So this is the first part of my presentation. We basically need to basically go through the evolution. We need to basically go through the historical background. I hope so you can see. Well, I hope so. Okay, I will try to explain. Okay, so solar cell or photovoltaic device is basically depends on photovoltaic effect. Okay, and this phenomena is basically introduced in 1839. Okay, this is the first time we basically gone through this thing, photovoltaic effect. Okay, and then later on, the first device that we have is basically in 1883 by Charles Fritz. This is the first device that we have related with the solar cells, and this device has basically efficiency around 1%, 1% efficiency. Okay, but the first practical solar cell related with the silicon-based solar cell is basically prepared by Bell's lab in 1954, and they reported their efficiency around 6%. This is the first practical device that we have. Okay, and after that, in late 1950s, we introduced this device in the satellite as well, and after that, we have seen an accelerated growth for this kind of technology. A lot of work related with this, and we have different variations of solar cells after that. Okay. And from the 1970s, we also seen that there is a big rapid fall in the prices of these devices as well, and that help also to make these devices commercial as well. So later, researchers basically get a major milestone when in 1982 they got basically 10% efficiency with the amorphous silicon thin films, and in 1985 they got 20% efficiency with the silicon-based solar cell, and this is basically introduced by the University of South Wales. They basically introduced 20% efficiency for this kind of device, and later, as I speak, from 1950s, we can see the accelerated growth for this kind of technology, and we researchers basically worked for different types of solar cells. So another type of solar cell was introduced in 1990s, which is basically the cadmium chloride thin film solar cell, and that has efficiency around 16%. And in late 1990s, there is another milestone achieved by this technology. We reached basically 1,000 megawatt worldwide. So along that, till now, we basically we can see many kind of solar cells, and we divide all these kind of solar cells in majorly four different generations. Okay, so if we talk about the first generation, this is basically called the wafer-based silicon generation, and in which we basically have two different types of solar cells. One is basically the microcrystalline silicon, and the other one is polycrystalline silicon with the different variations of efficiency. These are basically the efficiencies for the basically panel, not for the basically single solar cell, because we have for monocrystalline we have almost 26% efficiency for a single cell. Okay, for the second generation solar cell, which is called the thin film, we have amorphous thin film, cadmium chloride base, CIGS, and we can basically see the full name of CIGS, CDDS thin films, and with a different efficiency. We will later see what is the difference between them, and why we want to basically introduce new type of solar cells when we already have a solar cell. And for the third generation, we have multi-junction solar cells, quantum dot solar cells, dye-sensitized solar cells, perovskite, concentrated photovoltaic solar cells. And for the fourth generation, we have carbon nanotubes and graphene-based solar cells. Let's basically make a comparison between the different generations and between the different type of solar cells. Okay, we will mainly focus on cost, advantages and disadvantages as well. Okay. So when we talk about the first generation solar cells, we know that in this kind of or in this generation we have two different types of solar cells with efficiency which is very much higher, 20 to 22%, and for the other is 15 to 17%. The main problem for this kind of solar cell is basically the cost of material as well as the cost of process by which basically we make this kind of device. So we have a higher cost, but we have a higher efficiency as well. And when we talk about the second generation solar cell basically thin film solar cells. And for this, we have a major advantage for this kind of solar cells, which is basically cost effectiveness. Thin film means we basically need a very less material to be deposited and to get the electricity, to get the output. Okay, so in these type of solar cells, one of the advantages is basically the cost effectiveness, but there is a problem related with the material. We are utilizing cadmium, we are utilizing selenium, we are utilizing gallium. These all are basically the metals that are hazardous, or we can see the carcinogenic, that can cause cancer. So because of their toxicity, we have problem with these kind of materials. Okay, and when we talk about the third generation, for third generation we have multi-junction, quantum dot. We already seen all of them. We can see this much efficiency, which is very high, very high. But the problem with this kind of solar cell is we can't make it commercial. We can't produce this in a large size. Why? Because of expense, because of complexity of the manufacturing process for this kind of basically solar cell. Okay, and the other thing for these kind of solar cell is basically we will focus on perovskite, because many researchers are now working on perovskite as well, and they are basically aiming to basically have that kind of material under perovskite that is stable. The stability is the most problematic thing with perovskite solar cell, and also the toxic nature of the lead as well, because in perovskite we utilize lead. So this is another thing. So for the third generation, for the perovskite based solar cells, we have problem with the stability of the material. And for this, we basically introduce the other type of solar cells as well. For the fourth generation, we have carbon nanotube and graphene, but we have low efficiency with these type of devices. Okay, so this is the timeline. When we start from 1950s, as I already speak that we got the first silicon-based solar cell in 1950s. So after that, we basically moved towards the thin film solar cells from 1970s to basically we can see the 1980s and later 1990s as well. And we introduced the organic-based solar cells in 1990s as well, and then perovskite. And now many of the researchers are trying to basically build a hybrid cell. A hybrid means the organic and inorganic. They are trying to basically utilize organic and inorganic material to have better stability as well as have better efficiency to make them and to basically commercialize them. So what are the challenges? What are the factors that basically affect the efficiency, the basically voltage, the current that we will produce through these kind of devices? These are the different facts. We may have many other as well, but we will talk about a little bit about these factors. These are the main factors that basically contribute for the lowering of efficiency for these kind of devices. We have seen this temperature in our previous slides as well. In the table, we have seen that the temperature impacts much, even for all kind of devices that we have right now. Okay, why temperature affects? Basically, it by basically increasing the temperature, the resistance of the material got basically increases. So that basically hinder the transfer of charge, and that basically increase the recombination effect, and that basically reduce the efficiency of the device. And the other one is basically the installation angle. That is another thing to be considered while basically we are working with this kind of devices. We know that we have to get the better impact between the rays and the panel. Okay, so if the angle is not good enough to capture all the rays coming from the sun, it will not produce the power, the large power. Okay, so it should be the optimized angle with basically the sun. And if we have a fixed panel, it will not move along the sun, along the direction of the sun, and it will not basically provide us much power. And if we have a sensor here, and it can be rotate with the sun angle, then it will be good for us. And also location and cleaning as well, because if we have a panel under the shadow, it will not basically have much of the radiations. And also if we have dust particles along the surface of the panel, then it will reduce the basically penetration of the sun radiations through the panel. So it will basically lower the output. And another thing which is very important is moisture. As I already told you that in perovskite we normally use lead-based material. And why perovskite material has low stability, low lifetime? Because lead with moisture creates lead oxide, and that basically diffuses out from the material, from the main material, and that basically reduce the output of the device as well. And also with the moisture, the metal back contact, the metal contact that we have, the electrodes we have, that can be crude, and the material can be degrade, and once we have the degradation of the material, the main material will lost, and we will not basically have enough material to convert the solar energy into electrical energy. So by this we basically can see the country-wise total photovoltaic capacity, and not surprising for us, China is basically leading in this domain. And China, I think I can make the rough estimation, is basically China is holding almost 40% of the total market, global market for the solar cells. And the second main contender is basically the US, and then Japan, Germany, and rest are basically, including Pakistan and Mexico as well, they are trying to basically shift their production of electricity from the fossil fuel to the solar and wind energy. They are basically doing the things. For this, basically, we need the policy and other matters as well. And this is the basically projection, technological projected market share for different types of solar cells that we have. We already gone through the brief introduction for these kind of devices. Till now, at the present moment, almost 90% of the commercially available solar cells are consist of silicon based. Okay, and I already told you that for the silicon based solar cells, the main problem is their cost. And that basically make problem. So the future projection for 2030 basically give us idea that the dependency on silicon based solar cell will reduce, like 70% or 60% will depend on silicon, and the rest 30-40% will be for the other material, for the other type of solar cells. Okay, and that is why basically many researchers are now working for thin film based solar cells. What basically the lines that basically researchers are now working on these days. So we can see that many researchers are working for the new materials for the quantum dot and organic photovoltaic devices. Why? Because they are flexible, they are transparent, and because of these characteristics they can be used as a window, simple window. Yeah, and we can basically find when we Google it, where we can find many applications for these kind of devices as a window right now. And many researchers are trying to basically combine two or more semiconductors to basically cover the whole spectrum of the solar radiations. Now we are basically having materials that can basically absorb certain wavelengths of the radiation, not the others. So the researchers are basically trying to basically use two or more different types of semiconductors to cover the spectrum and to get the higher efficiency. And also many researchers are working for the new material like antimony selenide, tin sulfide, and CZTS like materials, because they have the low toxicity, they are abundant, and also they have the suitable band gap that is required to be a good absorber material. And also, as I speak, many researchers are now working on perovskite material as well. I already have experience with this kind of material, and now people are working to try to basically get the mixture of two type of perovskite material like 2D and 3D to get the better stability. They have the efficiency around 17%. They have the efficiency even around more than 20%. But the stability for this kind of device is just for 1 day or 2 days. I already experienced this. I made device, and on my first day, I experienced voltage around 0.79. But I kept this device for the 2 days, and when I basically measured the voltage again, it reduced to 0.5. So the main problem with this kind of material is the stability, and people are now working on them as well. And when we talk about the market outlook projection for the next few years, for the next almost 5 years, we can see that with this in 2022 in Mexico, basically this is basically for the Mexico. In 2022 we have 1.6 billion market revenue in Mexico, and for the 2030 the projection is basically 5.3, which is the increment of 16.1%. So that shows us that in Mexico basically the main focus is to utilize the renewable energy sources, and solar cell is one of them. So it is a hot topic to be basically worked on. And when we talk about the cost, so in this we can see that there is a rapid reduction of the prices. When we talk about the prices from 2009 to 2021, we have seen a lot of decrease, a lot decrease in the price for the solar cell. Almost 90% there is a decrease of price for this kind of technology, and that is basically shows us the potential for this research topic. And let's move towards another thing which is related with my project. I'm also working with thin film solar cells as well. And for my project, I'm utilizing a new material which is basically antimony selenide. And why I'm basically working on this material, why I'm so excited about this material to be used in the solar cell. We've already seen two major problems with the materials, with different materials. One is basically for thin films, we have toxic nature. One is the basically toxic nature. And the other one is basically the cost. We have seen that. For the first generation, we have a high cost. Yeah? For high cost, toxic nature, and also the availability of material as well. So I choose this material just because the availability of the material and also the price of the material. As you can see, this is selenium and this is antimony. And selenium and antimony has much higher availability as compared to gallium, as compared to indium, as compared to tellurium and all other elements, all other atoms that we basically normally utilize for thin films. And also the cost as well. We have low cost for selenium, for antimony, as compared to gallium, germanium, as compared to cadmium, indium, even lead, even silver. So this is the material that can basically give us some breakthrough in solar energy devices. And the properties for this material is very, very interesting. The band gap, which is the most suitable band gap to be used to basically utilize this kind of material as an absorber layer in the device, is 1.1 to 1.3. And a few minutes before this seminar, I got a good news from Dr. Meagle. Basically, I made this material, and for my material, I got the value, band gap value 1.17, which is perfect for this kind of, yeah. Absorption coefficient, which is basically a very important factor to be considered. It has a high absorption coefficient value, greater than 10 raised power 5, and that makes it suitable. Carrier mobility, carrier lifetime, we have good both of these for this material. Electrical conductivity, it has a good electrical conductivity. And for the optical properties, when we compare this material with the other chalcogenide material, we can say that this is the most efficient absorber material we can utilize for the solar cell. And another thing, which is the thermal stability, we have seen that the temperature basically degrade or affect the efficiency and the output of the device. So we have stability for this material, which is basically up to 400 degrees centigrade. Low toxic as compared to cadmium, even for the as compared to the lead as well. And we have seen that it is much abundant than the other materials, and also the low cost. So this is very interesting. The main problem related with this material is the structure. It is this basically material is we can say that is very choosy, is very moody material. It gives us output if it is appropriately made. If we have ribbon-like structure vertically, not horizontally. If we have this kind of structure in our material, we will have response, but not enough, not good. We need to have a vertical ribbon-like structures in our material. And you can see in my SEM images, we have cylindrical, vertical cylinders that basically giving us hint that we got something in our material, and we just need to basically work more on this material to optimize it, and then we can utilize it in the device to get better output. So this is what I need to present, and all rest basically, oops, it's not working. The references. Thank you so much for your attendance, and thank you so much for inviting me in the seminar. Thank you.
Well, it's time for questions and answer. Today, for encourage all of you, will be every participation of you will count double. Yeah, in English, of course. Here's the first one.
Hi. Hi.
Yes.
I have a question, but I don't know if it's totally related with the subject of your presentation. But the other day I was on the internet and I watched a video where they say that in China they've already created a PV cell that could be installed as a window. I mean, it was like a glass material, so I don't even know if that's possible. And
Yeah, it
I
is
didn't
possible.
check it to see if it was real, but
Yeah.
assuming it is, how could that work? I don't know.
Yeah, I already mentioned this, that now many researchers are working to have one material and two usage, to basically utilize these devices as a window as well as to get output from this kind of material. We already seen this, and I already mentioned that you can Google and you will find a lot of research on it. You will find a lot of research not only in laboratory but actual implementation in the buildings as well, and you already mentioned that. So it is possible, and now people are working on, even people are now working on smart glass. This is called the smart glass as well. Yeah, exactly. Yeah.
Okay. Who's the next?
Hi.
Yeah.
Well, first of all, thank you for your presentation. I truly like it. I want to ask. I have seen a lot of people that, well, they are not all against these panels, but they say that it should be better if we invest for more in nuclear nuclear energy.
Nuclear energy, yeah.
Nuclear energy. Sorry.
Yeah.
Yeah. So, because a lot of countries, including Spain, have made a lot of these enormous solar farms, and not a lot of people are so much a fan of them. So I would like to ask you, do you think that it will be at some point equal the efficiency of the solar panels such as the nuclear energy?
Okay. Let me go towards my slide and then I will respond to you. The previous, yeah, okay, yeah. For the nuclear energy, there is a risk involved, and I don't remember the exact year, but we can make sure we can basically make sure the year as well. There is a problem happen, I think, in Japan, or I don't know the exact even country as well. There is explosion inside the nuclear reactor, and they already abandoned all their reactors just because of this. So nuclear reactors, yeah, exactly. So nuclear reactors and nuclear energy give us electricity, give us energy, give us output, but it involves the cost plus the risk as well. And the other part of your question is basically, can we meet the efficiency and the output with the solar cells, with other like with the nuclear energy or not? This is the second part of your question, eh?
Yeah.
Yeah. So, so with the future projection, if we are depending upon this kind of technology, we certainly say that we will basically do this. We will have that much output from the devices. And the latest devices that basically publish in the new researches is basically having efficiency around 25%, 30%. So, and even I have gone through you a device which is multi-junction, and that has efficiency around 47%. But the main problem is the complexity of the process. But if we make it better, if we make the procedure better, we can make it commercialized, and we can basically compete the other kind of technologies with solar cells. Yeah, it has potential.
Oh, thank you.
Just a minute.
Thanks for the seminar, and my question is, what is your perspective of these technologies in about 10 years? For example, will we be able to use better these technologies, or we're going to have to create new technologies or devices for this kind of energy?
For basically this kind of technology, yeah, we may need to basically prepare new kind of devices, but that will fall under the umbrella of solar cell technology. Okay, but for the next 10 years, as the future projections say it, we have better future with this kind of technology. So why we are working on this kind of technology? Because we have a strong belief that it will work for us for the next years. So I hope so, and we all hope so, that it will work. Yeah.
Okay, thank you.
The gentleman first.
First of all, thank you for the conference. I'm very happy to know that inversions in solar energy are increasing. And I have a lot of questions, but I have to mention first the elephant in the room. That is the store. How do we store all the energy that solar energy systems can produce? Because sometimes they produce a lot of energy that we cannot even use. So how can we store all this energy? Have been an advance in batteries that can store that quantity of energy.
Okay. Yeah. So as when we basically were discussing the challenges that we have with this kind of technology, I mentioned that we may have many other challenges as well, and the storage of the energy is one of them. And so we can say that the researchers working on this kind of technology basically are also working on the storage as well. We have seen a lot of advancement in the batteries as well, like dry batteries, like lithium-ion battery, which is one of the most promising battery that can store this kind of energy. So we have advancement in that domain as well, but we are not basically able enough to basically store all of that. We are having surplus, but we are trying to basically remove the deficit as much as we can.
And I have a second question. This is more a curiosity.
Okay.
For example, if I decide tomorrow to install a solar energy system in my house,
Yeah.
what is the most probably type of panel that I can afford in a store or something like that?
Okay. Yeah. So we mainly 90% of the market is basically based on silicon-based solar cells. When you go out and when you try to buy the device, the solar panel, that is basically made with the silicon. And for the silicon, we have different kinds like monocrystalline, polycrystalline, like amorphous. And the price for these panels will vary because of the output. Monocrystalline are much higher in price because of they have high efficiency. So it all depends the utilization of the energy in your house or the building that you want to basically install that panel. Even I can see in market there is availability of thin film solar cells as well, but that will cost. So the major portion of the market is silicon based. So when you go out, you will find a lot of options related with the silicon and less with the other. So silicon is basically.
Okay,
Yeah.
thank you.
Thank you. Monocrystalline, polycrystalline, or amorphous. Yeah, more cheap. Yeah, exactly. Yeah, depending upon the price. Yeah.
Thank you for your presentation.
Yeah.
At the beginning of the presentation, you have many efficiencies.
Yeah.
How do you obtain that efficiency?
What? How we basically take that efficiency?
Yes.
Yeah. So efficiency basically, what is the meaning of efficiency? What is the meaning of efficiency? Efficiency is basically how efficiently we convert the energy coming from the solar to electricity. Yeah. Okay. So if we know the energy coming inside the device, and if we know the energy coming out output as an output outside the device, we can compare it and we can have the efficiency. Yeah. So let's say if we basically giving 100 watt to the device and we are getting 1 watt from the device, then we can say that it is only a very less, let's say 10%. So this is how basically the incoming energy and the outcoming energy, with that we basically measure the efficiency.
Oh, then can you calculate it?
Yeah, we can calculate What?
With
You want?
with a formula?
with the formula.
No, it's a question. It's a specific question. Okay,
so you,
okay, yeah.
So you want formula?
Yeah.
Basic, very simple. Okay. Percentage efficiency is equal to the, let's say, output energy.
Can you use this?
Oh, okay. Sorry. It will be
Exacto. Putin. Cuidado. Oh. Ya, entiendo.
It's a simplest, basically,
yeah.
simple equation, a very simple
Yeah.
equation. The total output energy that we got as electricity form, and the total input energy that we have through solar irradiation multiplied by 100, we will get the percentage of it.
Oh.
Yes.
Okay. Thank you so much.
Thank you very much for the conference. I just wanted to ask something related about the service life of these devices. What's the service life of these devices, or is it increasing with generations? Because as we can see in the next slides, the efficiency is not really like related with the generation. So is the service life
Okay.
related?
Let me comment on this. So for the first generation solar cells, silicon-based solar cells, that is we have in commercially available as well. A normal lifetime for a one panel silicon base is almost 25 years, which is very
Okay.
high. Yeah. But if we talk about the other, especially whenever we talk about the lifespan, I always mention the perovskite because it is a hot topic for me as well. So perovskite material has a very low lifespan, maybe 1 day or 2 day or couple of hours. Yeah. And for the thin films, yeah, it depends upon the material. We may have the efficiency retained for a couple of days, for maybe week. Okay. Yeah, but it is increasing day by day. We have higher efficiency for the first generation solar cells. We have 25 years is a much bigger time, but we want to develop and to increase the lifespan for the other type of solar cells because we want to reduce the cost as well, to make it commercial and to be useful for all the persons.
Thank you.
No problem.
Hi, good afternoon. I have a quick question about your new material.
Yeah.
I think that's antimonium.
Antimony ceramide. Yeah.
So you say that it's very important that you get the desired direction of the structure.
Yeah.
How do you manage to do that?
Okay, yeah. So basically, the main objective of my research as well to get the better electrical properties with my material, and to do so, I need to basically control the structure of the material as well. And to control the structure of material, we are utilizing the process, the procedure that enable us to basically control the growth of the material. So yeah, so we are utilizing the thermal evaporation method. That is, I think, more appropriate, and with that we can make sure the growth of the material, and that can basically give us a promising structure that we need. Yeah.
Thank you.
Yeah.
Good afternoon. Thanks for your presentation.
Okay.
My question is about the management of these devices when they reach their life cycle. For example, you have a solar cell of silicon, one of cadmium telluride, and one of your material, antimonium selenide.
Yeah.
Each one of them have a specific treatment when they reach their life cycle?
Yeah. So for basically the silicon-based solar cells, we basically utilizing them from over the years, and we have a lot of trash for this kind of panels, and I don't remember the exactly technique to basically recycle them. I don't know, to be honest, but we have techniques to basically tackle them and to recycle them. For the cadmium telluride and for the antimony selenide, for the cadmium especially, cadmium is basically the carcinogenic metal and is a toxic material, and to basically reduce the effect of this kind of heavy metal on living organisms, we have some kind of techniques like basically burying them inside the Earth's surface. Maybe this one. So we have different techniques, not for the recycling of this kind of material. For the silicon we have, but we can control the effect of this kind of metals.
Thank you so much.
Primero, levantó la mano.
Okay, first of all, thanks for the conference. My question refers to the second slide where compare the production of different energy source. Do you know, have an idea why the hydropower has decreased along the time, if it is a clean or renewable energy? I expect it will be stable at least. There no exist new places, ambiental impacts, efficiency, or what's the reason of the decrease?
For the hydropower, basically we required enough resources like money. To build a hydropower, to build a dam, it required a lot of investment, and also the maintenance as well. We need to basically invest on the maintenance of the material of the dam, and also for the functionality of the dam as well. So because of that, the investment is, I think, the main point. That is why we basically see a slight decrease in this as well. A slight decrease. In my opinion, this will be a point to basically give reason why there is a slight decrease in the utilization of hydropower. Yeah.
Okay, thanks.
Thank you.
Hi, Yousaf. How are you? Yousaf, I have a question. As a material designer, we are trying to make and design new materials for the solar cell, and we are trying to design green materials with the earth friendly. And if we know your material is so toxic, and I want to know what you to decide chose this material. Okay. And even so, yeah, this material has 1.5 efficiency report. And why your decision to choose this material, please?
Okay, so first, half of your question is basically the toxic nature of the material. So basically, as I mentioned that thin film solar cells, we are working on thin film solar cells from 1990s, and cadmium chloride based solar cell, basically the highest efficiency reported solar cells for this kind of for the second generation solar cells, and we have the basically commercialized solar cells as well related with the cadmium chloride. In comparison to cadmium chloride, antimony selenide has less toxicity. The toxic nature is related with the selenium, and when it is in elemental form, when it is in atomic form, when it is in the compound form, antimony selenide, its toxic nature even gets reduced. Yeah, so that is why we are utilizing. And the second is, you mentioned that 1.5, it's not the correct one. The highest reported efficiency for this material is 10.57. 10.57 is the highest reported efficiency for this material that I'm working on. But as we saw the characteristic of my material, we are expecting much higher output than this, much higher, because of optimal band gap, because of absorption coefficient, because of transfer, and also the lifespan. So with this, we are expecting much higher output from this material as we have. So that is why I'm working on it.
This efficiency is a theoretical efficiency? Or
No, the experimental one. 10.57 is the experimental highest efficiency. Yeah.
Hello, very nice presentation.
Okay.
I wanted to ask what are the benefits of the material you choose, antimony selenide. Is it more efficient? Does it have a longer lifespan? And could it be implemented in the form of smart glass?
Okay. If we get ultra thin film with this material, and if we optimized the structure of this material, we got output, we can utilize it for the window. If we got, because when we have a ultra high thin film, we have more transparency, and when we have more transparency, we can utilize in window. Okay, first. Secondly, what is the benefits of this material?
Yes.
Yeah. So benefits are listed here. All are benefits are listed here. Because of optimal band gap, or because of absorption coefficient, because of carrier mobility and all that.
Okay.
That is why.
Thanks a lot.
Thank you so much. Because I was not expecting that all of you will ask in English. But you all. Yeah, thank you so much. Thank you so much. Thank you so much.